Hi students, I'll try in this educational video to make a tutorial showing how to analyze a loaded portal frame in order to determine the normal force, the shear force, and the bending moment diagrams. Of course, as simply and as clearly as possible. Okay, let's go. Well, let's consider a dual pitch portal frame, ABCDE, that's the joints. Of course, we have the left hand and the right hand columns and rafters. And we have the characteristic dimensions of this portal frame. The span S is 7 meters, the eave height is 4 meters, and the apex height is 4.62 meters. This dual pitch portal frame is supported at the bottoms of the columns at the point A and E by pin support, and we have an internal pin at the joint between the left hand and the right hand rafters. Let's consider also that a uniformly distributed load of 5 kN per meter is applied on the rafters of this portal frame. First, we have to check the determinacy of this problem. Second, we have to find the reactions at the supports A and E. And third, we have to draw the normal force, the shear force, and the bending moment diagrams for both columns and rafters. Okay, for the determinacy checking, we have our frame, our structure, and here let's consider M the number of members, R the number of support reactions, G the number of joints, and C is the equations of conditions. It's equal to 1 for each internal pin, and it's equal to 2 for one internal roller. So here M, the number of members, is equal to 4, 2 columns and 2 rafters, and here R, which is the number of support reactions, it's equal to 4 because we have horizontal and vertical reactions at both pin supports, and we have G, the number of joints, equal to 5, A, B, C, D, and E. And the equations of condition C is equal to 1 because we have one single internal pin. So here, if 3M plus R is equal to 3G plus C, our structure is statically determinate, which means that the number of equations is equal to the number of unknowns, so it will be simple to solve. For more information about the determinacy checking, you can see the first video in this playlist. And here 3M plus R is equal to 16 and 3G plus C is equal to 16, so 3M plus R is equal to 3G plus C. So our structure is statically determined. So as we indicated before, it's simple to solve the problem since the number of equations is equal to the number of unknowns. Now for the reactions determination. So we have our problem, and we have at the point A and E, which are the bottom of the columns, we have horizontal and vertical reactions, AH and EH, and AV and EV. Well, we will convert also the UDL into a point load UDL multiplied by the span S, and we will apply the equilibrium equation of moment at the point A. That will permit to determine the vertical reaction at the point E. So if we consider the clockwise direction as the positive direction of the moments, and we apply the equilibrium equation, we will obtain EV equal to 17.5 kilonewton. And now we will apply also the equilibrium equation of vertical forces in order to obtain the vertical force at the point A, AV. Let's consider the positive direction of forces, which as the upward direction. The application of the equilibrium equation will permit to obtain AV equal also to 17.5 kilonewton. It remains to determine the horizontal reactions at the point A and E, which are AH and EH. In order to determine these horizontal reactions AH and EH, we have to notice the symmetry of the problem because this symmetry will simplify calculations. As we can notice, we have a symmetrical dual pitch frame, so we have a symmetrical geometry of our frame. We have also symmetrical loading. We have a symmetrical support, two pin supports at the point A and E, and we have an internal pin at the apex C. The apex C is located, let's say, at the mid of our frame. These symmetries will induce a problem symmetry, and our problem can be subdivided into two parts: right hand part ABC and the left hand part EDC. The right hand and the left hand parts are equivalent. So let's consider the right hand part of our frame ABC, and here C will have two reactions, horizontal and vertical reactions, and the UDL will be converted into a point load equal to UDL multiplied by the half span, and the point load is located at the fourth of the span from the point B. So here, if we apply the equilibrium equations of moment at the point C, we can determine the horizontal reaction at the point A. So let's consider the clockwise direction as the positive direction of moments. We apply the equilibrium equation and we find AH equal to 6.63 kilonewton. Now, if we apply the forces or the equilibrium of forces along the vertical direction, we will obtain the vertical reaction at the point C, CV. So if we consider the upward direction at the positive direction and we apply the equilibrium equation, we will find CV equal to 0 kilonewton. And in the same way, we apply the equilibrium equation of forces along the horizontal direction in order to determine CH. And here we consider that the positive direction is the direction from the right or from the left to the right. And here, if we apply the equilibrium equation, we will determine CH as 6.63 kilonewton. Now, I will try to determine the forces and the moments at the point B, at the joint B, and based on the free body diagram, if we consider here the column AB, in order to make equilibrium, we should have a counter horizontal force and also a counter vertical force. And since we have a fixed joint at B, we will have a moment at B. Now, for the point B, or if we transfer from the point B, consider it belonging to the column, to the point B, consider it belonging to the rafter, we will have the same forces but in the opposite direction, and the same moment but also in the opposite direction. If we apply the equilibrium of equations or of moments at the point B, we will find finally the value of the moment at B, which is equal to 26.52 kilonewton meter. Well, now I'll explain how to determine the normal force, the shear force, and the bending moment diagrams for the column. So we have the column, and we have the forces, the horizontal and vertical forces, and the moments applied on the points A and B of this column. And based on these forces, we will try to elaborate the normal force diagram, the shear force diagram, and the bending moment diagram. For the normal force diagram, it's clear that the column is subjected to a compression of 17.5 kilonewton. So the normal force diagram will be like this. And for the shear force diagram, we have a shear force equal to 6.63 kilonewton applied at the point A. And here, don't forget that the variation of the shear force along the longitudinal direction of the column is equal to minus the applied force. So the shear force diagram will be minus 6.63 kilonewton over the column. And at the point B, since we have a shear force of the same magnitude, 6.63 kilonewton and applied in the opposite direction. So at the point B, the shear force will drastically decrease to 0 kilonewton. Now for the bending moment diagram, we have a pin support at the point A, so the column is free to rotate at the point A. So we will have a bending moment equal to 0 kilonewton meter. And since we have the variation of the bending moment along the longitudinal direction of the column is equal to the shear force, in other terms, the bending moment is the integrate of the shear force along the longitudinal direction of the column. And since the shear force diagram is constant, which means a 0-degree function, the bending moment diagram will be a 1-degree function like this. And the maximum value in of the bending moment in the neighborhood of the point B will be the area of the shear force diagram, which will give minus 26.52 kilonewton meter. And don't forget, we have a bending moment, a positive bending moment of 26.52 kilonewton meter. So the bending moment will, at the point B, will decrease drastically to 0 kilonewton meter. Well, now I'll try to explain how to determine the normal force, the shear force, and the bending moment diagrams for the rafter. So here we have our rafter BC with the forces and the bending moment at the point B and C, and the UDL applied on the rafter. So we have an angle alpha, which is the inclination angle of the rafter, and we determine the angle alpha as 10 degree, and we can determine also the length of the rafter BC as 3.55 meters. Now we have to change the frame of reference horizontal vertical to x and y. X is the longitudinal direction of the rafter and y is the transversal direction of this rafter. And here we will have bx, and bx based on trigonometric conversion, we obtain bx equal to 9.57 kilonewton. In the same way, we determine by as 16.008 kilonewton. At the point C, we have cx determined by a trigonometric conversion as 6.53 kilonewton, and we have cy determined in the same way as 1.15 kilonewton. And we determine the UDL parallel based on both a conversion of the UDL into a point load and a trigonometric conversion, and we obtain UDL parallel as 0.86 kilonewton per meter. And the UDL perpendicular is determined in the same way as 4.86 kilonewton. Now we have our rafter subjected to bx by at B and cx cy at C, and UDL perpendicular and UDL parallel along the rafter BC. Well, now I'll explain how to determine the normal force, the shear force, and the bending moment diagrams for the rafter. So we have our model that we constructed, and first we will determine the normal force diagram on the rafter. So we have here at the point C 6.53 kilonewton in the opposite direction of x, so we have minus 6.53 kilonewton, and we can predict the normal force at B as 9.58 kilonewton. Here we have 9.57 kilonewton. This is normal due to the rounding errors. So finally we can draw the normal force diagram. Now for the shear force diagram, we have at the point B 16.08 kilonewton, and we can predict the shear force diagram at the point C as 1.17 kilonewton, but here we have 1.15 kilonewton, and this is also normal to the rounding errors. And we can draw finally the shear force diagram. And we have the point D where the shear force is equal to 0. We can determine the location of this point D using this equation, and finally we obtain D equal to 3.31 meter if we consider that the origin of calculation is the point B of the rafter. Now, for the bending moment diagram, we have a minus 26.52 kilonewton meter as bending moment at the point B, and at the point D we have a shear force equal to 0. So based on the fact that the variation of the bending moment along the longitudinal direction of the rafter is equal to the shear force, so when the shear force is equal to 0, the bending moment is an extremum, which is a maximum here. So we have to calculate the bending moment at the point D. Since the bending moment can be also seen as the integrate of the shear force along the longitudinal direction of the rafter, so the bending moment at the point D can be calculated as the bending moment at the point B plus the area of the shear force diagram, the area before the point D, which is a positive area, and finally we obtain a bending moment diagram at the point D equal to 0.09 kilonewton meter. In the same way, we can determine the bending moment at the point C as the bending moment at the point D plus the area 2, which is the area of the shear force diagram after the point D, which is a negative area. And finally, we obtain the bending moment diagram is equal, or the bending moment at the point C is equal to minus 0.05 kilonewton, and it should be 0 because at the point C we have an internal pin, but here it's normal because we have a rounding errors. So finally we can draw the whole bending moment diagram. It's all for this video. If you have any questions or remarks, please do not hesitate to mention it in the comments. Thank you very much for your attention.